All right, so we'll get going here. A couple of things before we kind of dive into material. So this data, if you're still not able to kind of get it up and working from your PC, I've got a couple of things that should cover most people. The first, I feel like I've gotten a lot of people, I know I said this, so this is a crucial part. You're getting an error that it like can't access or needs administrative rights. You can only open up files from your own OneDrive. So you can't open it up from your downloads. You can't open it up from your desktop. It has to be on your OneDrive. Okay? So make sure that you're trying to do that. Also, some devices, if they have limited capabilities, I was told by the tech people that if you can get to this point and it's not opening up, right? I think it calls like an ICR file or something like this up here when it downloads. If you go to account settings, if you've already activated Citrix, you can click change. And there's this use light version, and that might solve a lot of people's issues. I don't understand kind of the backside of the tech of why, but it should have all still the same capabilities. It's just the interface will be a little bit differently, but that might solve some people's issues as well. I went back too far. If you can get this far, right? If you can get this far and just can't get Stata to open, then maybe using that light version will work. If you can get the program open and you can't open files, it's probably because you don't have them on your OneDrive. And if you're still having any other issues, had a lot of people stop by yesterday during office hours, and everyone that stopped by, we actually got it worked out. It's a lot easier for me. You've all got different devices. You've all done different steps that I don't know about by the time you can ask me a question. So stopping by my office hours is a good way to kind of get that up and running. I think I said last class, I was going to, since we didn't have Labor Day, I'd move my office hours to Friday this week. Fortunately, I usually leave Fridays open for meetings, and a bunch of meetings popped up, so I won't be able to be there. But I will be in my office from 10 to 1 tomorrow, so same amount of time, just kind of shifted earlier in the day. So if you want to stop by, you're still having kind of issues with Stata, we can screen share. I can walk you through it via Zoom tomorrow if you want to do it that way. Because after class today, once I get back to my office, I'm going to put up that very first problem set. So I'll show you kind of what it looks like. I forgot to drag it onto my OneDrive. At least, so I went back. I have a version of it. Oh, come on. Got a bunch of templates that I then changed. Let's see. Problem set for wrong one. It's this folder. Problem set 1. Don't want to show you the solutions. There we go. So it's 10 questions, right? Each one worth a certain amount of points. So basically, you're going to use Stata to answer every single one of these questions. I'll give you a data set, and I'll show you here in a second. We'll talk a little more about Stata data sets. Up to this point, we've imported Excel, imported CSV, so that we can convert them into data, like data behind the scenes that Stata is using. I'll just give you a Stata data set here, so it's as simple as kind of going to File, Open. You can open the data set. So when we're walking through these do files, which we will do early on in the class today, anytime I have like import or use, I'm opening a file, you can't run that line of code. Why? Because that's pulling it from my computer. So you're going to have, it's the only thing in that do file you won't be able to execute either on your own or in class. So that's why I showed you how to set up that global kind of path variable. So that's why the code I put path, so that you could just put in what your iDrive file path is. And if you're having issues with that, once again, this is the thing to kind of work with me. I don't have a lot of time before and after class, so office hours are going to be a really good resource for that. But once I post this problem set with the data file, you'll download the data, put it on your OneDrive. You can start working through. And basically that review of statistics file should have everything you need to answer all of these questions. I'll show you a different, the NBA height data today, but you shouldn't need anything from that in order to answer these questions. Just that review of statistics do file. And we won't quite get through it based on my last section. We're going to fall short a little bit of my expectations this week. And this week's material review will kind of bleed over into Tuesday. So it'll probably take like the first 15, 20 minutes Tuesday to finish up what we don't cover today. But you can get pretty far. You could probably get to like question 8. Yeah, you can get to question 8 for sure, based off what we've already done prior to even today. Okay, so start working on that early. I'll give you 2 weeks to do it, so it won't be due. This is an old one, so ignore that. But the one I post will be due 2 weeks from today. So basically, before class starts, 2 weeks from today. I would not hold off on working on it later, because the further we get from when we actually cover the material, the harder it's going to be then to kind of jump in and do it in Stata. So start working on it early. That way you have plenty of time to kind of ask me for help. You know, as long as you come and ask me, I'll help you through these. Like I want you to get as many points possible on these problem sets, because you do have a lot of time. You have all your resources available, but also this course, you know, we're going to go through a lot of theory. What's also really important is how do we take what we know about statistics and apply it to actual data? That's what these problem sets are meant to do. Okay. So you'll see that pop up this afternoon. I was going to put the first quiz up this afternoon. I don't want to, because I think the last couple of questions, we're not going to quite get there today. So I'll get that quiz up after class next Tuesday, and you'll have kind of a set time. I'll tell you the due date once in class next Tuesday. I want to look a little bit at the problem sets, make sure you guys have enough time to get on there and do that. But I will put up after class today the practice problems, so you can start looking at the types of questions you can expect to see on that quiz, kind of working through them, make sure that you're able to solve them. Practice problems will look pretty close to the quizzes that you take on campus. Okay. Any other questions for me before we kind of dive into material? I think that should cover everything on my end. How many of us got Stata working? Okay, decent number of most of us. All right. Also, if you're having trouble with the Wi-Fi in here, does anybody have trouble in class ever? I was told that if you're sometimes your devices default to EduRoam, and if you switch over to IU Guest, sometimes it can be a little bit quicker. So if you're ever having kind of Wi-Fi issues in this room, switch it over from EduRoam to IU Guest, and sometimes that will help. Yeah. The problem set. So when is the problem set due? 2 weeks from today, before class starts. Yep. Like I said, this is an old one I had, and I didn't have it on my OneDrive, the one that's going to get posted. It actually looks a little bit different even than that one, but the general length is about the same. All right. So that being said, any other questions before we dive into material? Okay. So to kind of remind us where we left off, we had this idea that we were saying, okay, if I were able to sample from some data, so the data we're going to use today is a bunch of different players and their height, NBA player height data. If I could take a random sample of 30 of the people in the data set, calculate the sample mean, write that number down. Take another random sample of 30 people, calculate the sample mean, write that number down. Keep on doing that like 1,000 times. I would then have a data set of 1,000 different sample means. If I look at those sample mean, the mean of those sample means, it will always be the original population mean of the data I was sampling from. The variance of those 1,000 sample means will always be the original variance of the data I sampled from divided by my sample size. Okay? So this is going to be, we'll see this play out. I'll run through actually some simulations to prove this to you, but these two things will hold if we have purely IID, identically and independently distributed, just basically a fancy word of random, completely random samples. These will hold. Okay. So I'll show this to you before I walk through the code, but basically you can prove this to yourself. So I had a data set laying around, had a bunch of NBA players' height. It was population data. I could very quickly find the population kind of mean. Forgot to put a bar over there, but this is the population mean and the population variance. So what should be true is when I take 1,000 random samples, even if it's of size 10, those 1,000 different sample means should be equal to the true population mean of 79.14. And the variance of those sample means that I found should be the original variance of 12.59 divided by 10, or 1.259. So we'll see if this actually happens and state it here. And once again, sometimes I'll show you things. So I mentioned that problem set is just the review of statistics do file. I'm going to show you some of the power of Stata here. I by no means am going to expect you guys to be able to do this even by the end of the semester, right? But how many of you have kind of had any experience in R? I know a few of you have mentioned it to me. Yeah, a handful. So, you kind of can see it has similar capabilities as Stata. We can see how far we can actually take this. So here's where I've got my global being set. So what this is doing is saying, look, we all want to start out, if you were following along with me, using that NBA data.dta. So that .dta says this is a Stata data file, right? And basically, I think it's I don't know these, like, this is technically not exactly correct, but like Excel, the same data set in Excel is much larger, and Stata has a way of condensing the data so that they're like smaller, fewer bytes, and doesn't take up as much room. And then it can work with the data quicker, essentially, so it's not taking up as much space. So I've got this already as a Stata data file, but mine is sitting in a folder under fall 2024, this section, all these other different things. If you want, you could just drag and drop it onto your OneDrive, and then I think it would literally just be I semicolon, and that's all you would need as your path. And then you could run this, right? But if you didn't, just one thing I want to kind of point out is you can always, anytime I have like a use, so use just means open essentially, I can always do this from the interface. So I can go to File, Open. I then wanted to open that NBA height data, so I'm going to click on that, hit OK, and it runs this line of code for me. Now, and it's opening up the data set, okay? Now, I could copy and paste this over into my do file, just so that I kind of always have that same use command. There's going to be one issue. When I first start out and I open up a data set, it stops here. Notice my do file, I've got something else that I put here, which is the word, I put comma clear, right? Because anytime you open a data set, let's say I didn't put that, now I'm going to assign my global to be where my iDrive, where the files are. I'm going to then use, that was what opened up that data set. So that was the command use, just opens up a Stata data set. Now, if I don't make any changes, it can open it up just fine, right? But if I start to make changes, like I only want to keep 2 of the variables, so I basically just only kept the player and their height. Now, if I go back and try to run this line of code and open the data, I get this error, right? So why am I getting this error? It's because once you make a change, Stata recognizes they don't want you to make a mistake and try to like get rid of all your changes, right? So you'll have to clear out the old data. It needs you to like confirm, hey, you're trying to open another data set. Are you sure you want to get rid of everything you've done? So I am sure. So you can do it 2 ways. You can put comma clear. And now when we run this line of code, now we don't get an error message. It cleared out the old data, uploaded the new one. I had someone ask me last class, you might see this, I don't know, if you're Googling or looking for help things. You can also just put the word clear up here and it clears out the data set. Does the exact same thing, just 2 different ways of doing the same thing. So once we have this data set loaded, right, I'm just going to keep the variable I'm interested in, which is just the player's name and what their height was. I think it's their name. It's made as an ID number. No, it's their actual name. Okay. Once I do that, I'm going to summarize this. I kind of typed the full thing out, but remember, we can shorthand a lot of these commands. So like generate, gen, summarize, sum. So this is just going to give me my summary statistics. So I can see here that this height variable has a mean of 79.14 and 12.59. Those are the values that I had in the slides, right? Because I could look at the data ahead of time. If I then am going to create a program, so I'm going to clear out any existing programs. It shouldn't matter on this computer because we're starting from scratch, but it's good practice anytime you're going to want to use your own program to clear out the programs. I'm never going to expect you to make your own program. There's probably stuff later on the semester you kind of could. So I guess if you're really interested and you want to put some extra work in, you could use this method, but it'll never be expected of you. You can define these programs. They're basically lines of code that as soon as you then just kind of tell it the name. So I defined this program as y bar. This essentially will calculate a mean for a variable and then store it. That's all this code does. So you don't have to worry about, like I said, I'm not going to make you do this on a problem set, but essentially this is going to go through. It's going to open up that height data set. It's going to randomly sample 10 people from that data set, calculate kind of the mean of this height variable, right? Once it calculates the mean of that height variable, it's going to store it, right? So that's all this program does. It randomly samples, calculates a sample mean, stores the sample mean. So I'm going to define this program by running this code. Right? So anytime I say program, it'll everything here. Okay, it now has this program y bar, basically calculating a sample mean, stored behind the scenes. Okay, so it's sitting there. I can use it whenever I want. So the next line says, okay, look, and let's make this so that things are kind of on one line. And I think we'll still be able to see it a little bit. So there we go. So don't worry, once again, I'm not going to make you reproduce this, but all this line is really saying is, look, I want you to take this function that I kind of called y bar, right? And I want you to go through this function 1,000 different times. So at the end of this, I'm going to have this new kind of variable I'm calling means, which will be a new data set that has 1,000 different sample means in it. So it's going to run that, it's going to randomly sample 10 people, calculate a sample mean, store it in this means variable. Do that 1,000 times. Once we have 1,000 different sample means, so we're going to run that. What we'll see here is, okay, I've got my 1,000 different sample means, all random samples, right? Once I have this data, oh, I wanted to select my view file. There we go. I'm now just going to summarize that, right? And I'm going to find, okay, what is the mean of these sample means and what's the variance? And it should follow what I told you before, right? So we'll hit run here. Sure enough, the mean of my sample means is the exact, well, not the exact same, right? 79.14307. What was it before? 79.1434. Very close, right? If I think about the variance, oh, did I run the? Oh, no. So it should have been what? The original variance was 12.5659. So we said it should be what? 1.259. It's a little bit higher, 1.3, but it's pretty close, right? So why are they a little bit off? Well, for it truly to be kind of equal to the variance over the sample size, I'm just doing 1,000 simulations here. In theory, or the math says I would actually need an infinite number, right? So I can get close to proving this to myself, but the numbers are always going to be a little bit off. Okay. But I think this is a pretty good way of seeing that. I had some other ones. So not only is it that I only did 1,000 simulations why they're a little off, in order to, we'll eventually say that the sample means will have a normal distribution. They'll be centered around the true population mean, and the variance will be the original variance of the data we sampled from over our sample size. But that only holds, you might remember this from 370 or the equivalent. Well, how many observations do I need for that to be true? I think someone said 30, right? It's kind of this magic cutoff number. You know, you can go through the mathematical proof to show you that is the cutoff. So here I did 30, right? To kind of show you that it gets a lot closer when you run 30. So I'm going to clear it out. It's all the same code. It's just going to now randomly sample 30 people from the data and then do that 1,000 times, store it. We'll give it a second to think here. It's trying. But now we should still find that the mean of our sample means is the original population mean of like 79.14. Once again, it's a little off because I've got 1,000. No, I don't have an infinite. And then here my variance, it's a little bit harder to think about, right? Because I would have to be taking 12.56 and dividing it by 30, which should be about 0.4 something. Oh, yeah, that's what I'm getting here as well. And then we can even be more extreme. I can do samples of size 100. Now, they should still be centered around that same population mean of 79.14. But now the variance of my sample mean should be, what, 12.56 divided by 100, so 0.1256. We'll give it a second to think, and hopefully we'll see that that happens as well here. Okay. We're waiting. There we go. Okay. Sure enough, 0.1226. It's getting very close to that 0.12256. 79.135. That would round to 79.14. Looks like what I'm saying is this true, right? We're proving it to ourselves using the data, okay? So that's kind of the work that we did here. This is kind of a summary, there we go, of a lot of things I just said. And one of the things that we really need to be true when we're talking about these sample distributions, I already alluded to it, we need that sample size to be above 30, right? That sample size is above 30, we know it's going to be unbiased, where the mean of our sample means is the population mean, consistent, the variance of our sample means is the original variance over the sample size, and if we can get over 30, we know that our sample means will be normally distributed, right? So that's our kind of central limit theorem. We need a sample size over 30. The higher and higher our sample size gets, the closer and closer, like to a perfect normal distribution, our sample distribution, our sample mean distribution will be. So I always liked, I had like some really old textbook, and I just always liked this photo, so I kept it. But like, I like it because you can see, here's the original data we sampled from. These look like not even close to normal distributions, right? But if you randomly sample, like you do a similar thing, and then you graph out all your sample means, at sample size 2, they start to look quite a bit different. Nothing really looks normal yet. But even at 6, some of these distributions, you start to get the sample means are looking pretty close to a normal distribution. Now, I don't know if it's easy to see from out there, but this one's like still shifted a little bit. The mean isn't quite the exact, population mean. This one, you can definitely see there's some skew to it. But by the time you get to 30, all of these are nice, tight, normal distributions centered around that population mean, and the variance of each one is the variance of the original data over your sample size, okay? Just looking familiar, hopefully, sound somewhat familiar. So we already did all this, kind of skipped it ahead. So this is kind of the summary, right? We've already covered this, but I thought maybe we, different sections, I just wanted to make sure that we start at different points. So the other section, I might have started off in this slide because we had a little bit further with them. Now, one thing I wanted to go through before we keep moving, and I don't think I had this. Yeah, I don't have this in the actual do file. But what's one thing I said last class? We can get a nice quick snapshot of data. Does anybody remember a command we can use in Stata to do this? Sum. So sum gives us all that nice, like the mean. But if I want to get one of those like kind of nice distributions, right? Or a histogram, we said that the command was hist, right? So if I wanted to do hist of this means variable, this is going to tell me the distribution of my sample means. And I shouldn't say tell me. It's going to give me a little visual, and it won't be perfect because it creates a certain number of bins, but it's a nice like snapshot. Now, at a sample of size 1,000 or 100 here, right? I would imagine this is pretty close to a normal distribution, or at least it should be if the central limit theorem isn't full of, whatever. So sure enough, this is, hard to draw something almost as good of a normal distribution here, right? So anytime we get a sample size over 30, our sample means will be normally distributed as well. And we can prove that to ourselves kind of using these simulated data sets. Well, I shouldn't say data sets, simulated random samples, okay? Any questions? Or keep moving here. All right, I'm going kind of quick, like I said. Okay. Should be a lot of review, but if there's ever something I say and you don't remember it or just glossing over it and you have more questions, stop me. All right. So all of this, up to this point, when we're looking at the variance of our sample means, I was taking the population variance and dividing it by the sample size. Well, that's great, but the whole reason I had samples because I didn't have the population data. How do I know the population variance? So more often than not, all we're going to have is our sample variance. All right. So I have this working. So most of the time, we're not going to know what that population standard deviation is of my sample means because I don't have the original population data to know what the population variance is. So what am I going to do? I'm going to use my best estimate, which is just the variance that I see from my sample, right? So we're going to find the variant or the standard deviation or the variance of our sample means and fix this in my last section. I forgot to save it, but actually I might. There we go. I hate kind of when there's typos. And so this, without glossing over it, really here, this was supposed to be the standard deviation of our sample means, right? It's just that we notate it with an S now instead of kind of our Greek lettering because we're no longer calculating it using a population variance. We only had a sample variance. That was our best guess of what the actual population variance was, okay? But it's similar format, right? Nothing too crazy here. So if we're using instead this sample variance, anytime we standardize a variable, right? Remember last class, how did we standardize a variable, or how did we find how many standard deviations away it was from the mean? We just take the value, subtract the mean, divide by the standard deviation, gave us these nice z-scores, right? Well, the problem is we now are going to be dividing by not the true kind of population variance, but just our best guess, which was based off of our sample variance, okay? So if I try to standardize a sample mean by subtracting the mean of my sample mean distribution and dividing by the standard deviation of my sample mean distribution, I'm going to have some problems, okay? And in fact, I know I have this on later slides, but it might make more sense to do this before we get into this discussion now. So we did last class is we were just taking values, subtracting the mean, dividing by the standard deviation, right? That kind of standardized it, gave me this nice z value. What we're now going to have is what we're going to end up saying is a t value, right? So if I try to change my sample mean, if I try to standardize it, I need to subtract the mean of my sample means and divide by the standard deviation of my sample means. But we said, I don't know the population variance, so we kind of notated that with an S. What's the mean of my sample means? That's just the original mean of the data I sampled from. What's the standard deviation of my sample means? That was the square root of the variance, right? So we're trying to get a standard deviation. But what was the variance of my sample means? Well, I was using the sample variance as the best guess of what the population variance was over my sample size, okay? So there's going to be one problem when I standardize these sample mean values or try to create these what look like z statistics, but they're not, and we'll get to why in a second, which is, let's say I had a sample and the variance ended up being exactly, the variation that existed in the data was exactly the same as the variation in the population. When I find a population variance, and we haven't quite, I don't know, I think we went through this. So for a population variance, you add up all this deviation squared and divide by n. For the sample variance, we said you add up all the standard deviations squared and divide by, not standard deviation squared, sorry. We add up all the deviations from the mean squared and divide by not n, but, remember how we treat a sample differently? N minus 1 when you're calculating a sample variance. So even if I got a data set that perfectly matched up to what the population variance was, when I calculate a sample variance, I'm dividing by n minus 1. So I should have been, I'm always going to be kind of like having a slightly smaller denominator. And so it's always going to kind of inflate what this fraction is. Then I'm dividing by a larger number. It's always going to make my test statistic or my t value a little bit smaller, right? Even if I had a sample variance that was exactly the same as my population. So we need to account for this, right? And dividing by 9 instead of 10, well, here, I'll make it even more extreme. Dividing by 1 instead of 2 can cause a huge difference, right? If I take 10 divided by 2, I get 5. Divided by 1, it's 10. There's a 5, If I divide by 999 instead of 1,000, there's not going to be as much of a difference. So the larger my sample size, this idea that we're using the sample variance becomes less and less relevant. Like we don't care as much. But when we have smaller sample sizes, relying just on our sample variance with an unknown population variance can cause some distortions. So we'll want to account for that. So we're going to have to use, there we go. We're going to have to use the student t distributions, right? They are normally distributed, right? So it's not just one distribution. I know that I accidentally, a lot of the times, just call it the student t distribution. It is technically a set of distributions. They're all normally distributed, right? So their mean is going to be equal to their median, is going to be equal to their mode. They're symmetric. They're very similar to our standard normal, but they're going to be a little bit more spread out, right? So we're thinking about, comparing those, we're going to be a little bit more spread out. I've got a visual for that here in a second. Now, each student t distribution is going to be connected to what we call the degrees of freedom. All the degrees of freedom is n minus 1. And when we start talking about other statistics throughout the semester, we will have degrees of freedom for things like F distributions. You might have heard like chi-squared. I don't know what other courses you've taken, but there's different degrees of freedoms depending on what type of distribution we're looking at. But right now, it's easy. It's just n minus 1, right? So n minus 1 is our degrees of freedom. That I already mentioned, they're symmetric. It's a little bit more spread out. I'll come back to point 3 here in a second because I want to give you this nice visual first, right? So here's our standard normal distribution. If I'm saying that the student t distributions are a little bit more spread out, what that's saying is that the likelihood I see values that are like not many standard deviations away from the mean, right? So you can still think of t values the same as z values is telling you how many standard deviations away from the mean was the value you saw. With a student t distribution, those values that are like not many standard deviations away from the mean, not as likely, right? The probability is not as high. Notice my tails, though, is blue tail. It's a little bit fatter tails, which means seeing things that are further from that mean are a little bit more likely. So it's more spread out. Now, as I go to lower and lower sample sizes correspond to lower and lower degrees of freedom, I'm just getting a more spread out distribution, or another way of saying that, right, I'm getting like a flatter distribution. It's kind of flatter in the middle, and it's got fatter tails, okay? Representing that it's much more likely when I have small sample sizes from these student t distributions that I'm going to be seeing things that are further out from the mean, okay? Now, third point here that I skipped over was, okay, small sample sizes are a problem. Large sample sizes are a good thing almost all the time. And in this case, again, it makes our life easier. Once you get to a degrees of freedom of 100, you're only going to be off at the second decimal at most when you're looking at the differences between a student t and a standard normal distribution. So just a rule of thumb, like the way that we'll kind of treat it in this class, is anytime you get a sample size over 100, you can basically just use your standard normal to approximate. Okay, so as you get higher and higher sample sizes, this student t starts to become more and more like your standard normal. Once you get over 100, visually, if you had them drawn out, you couldn't even tell the difference. Okay, and we're dealing with data sets often much larger than 100. Do you have a question?
Yeah, so for the Q, you talked about the degrees of freedom, right? And it's essentially how far away it is from the mean.
So the degrees of freedom is just going to tell you which student t distribution you need to use.
Okay.
The lower the degrees of freedom, you're going to be getting a flatter middle, meaning it's less likely you see values near the mean. You're getting fatter, not flatter, fatter tails, yeah, which is telling you the likelihood of seeing values very far from the mean has gone up. Right? And the reason this kind of makes sense intuitively, if I chose, let's say my sample was of one person, if I randomly sample one person, I could see a height way far away. It's very likely I see someone maybe who's even 5'3", right? But if I take a sample of 100 people, to get a sample mean of 5'3" is very unlikely, right? The probability is much, much lower. So if you want to use those extreme points, like going from 0 to even 100 people, maybe that helps kind of sort of. Does that answer your question? Any other questions before we keep moving here? Okay. All right. So to make this point, so if I chose a value, remember last class, we were looking up like the probability associated with different z values. So I could take 1.96, I could go to my standard normal table and figure out the probability of seeing something to the right of 1.96, but under my standard normal curve, right? That's what that z table told us. So if I do that from a standard normal distribution, I get 0.025. Well, for these student t distributions, if I use that same value, am I going to get that same desired probability in my tail? Well, no, my tails are now fatter. So if I stay at 1.96, notice the area under my curve is going to be a little bit higher. And the lower the degrees of freedom, the fatter that tail, the higher that probability is going to be. So if I do want 0.025 from a student t distribution, I can't use 1.96. What am I going to have to do? Choose a value that's The area to the right under the curve, if it's 0.068, how do I get that down to 0.025? You guys are worrying me. I would choose a higher value, right? I need to get a value that's reducing the area in the tail down to 0.025. So I need to get a value that is to the right of 1.96 or use a higher value. Okay? So if I look at my student T table, and I have an actual file PDF, which has more degrees of freedom in it that you guys can kind of pull open and use, and I'll show you here in a second. But this tells me the different T values associated with a lot of those kind of benchmark areas in the tail, which I think will make a little more sense when we start talking about hypothesis testing today. But you kind of notice, if I want 0.05 in my tail, right? Well, if my degrees of freedom is only 2, I need a really high value, right? 2.92. If I have higher degrees of freedom, that value now can be lower and lower and lower and lower until I get to 100. Now it's almost the exact same. This last row says inf, means infinity. I probably should insert the symbol, not be lazy there. But notice these values are like hardly any different from 100 to infinity. If we truly did have a sample size or degrees of freedom of infinity, which, then we get, it's weird, right? Because there's sets of infinity, like different infinities can be smaller than other infinities. I've watched far too many YouTubes about this, right? But like if we did have an infinite number of sample size, infinity minus 1 is still an infinite set. We would actually have our standard normal distribution values. So anything over 100, we're just going to approximate it using the last row of our student T table, which gives us our standard normal values. So it's kind of nice about this student T table. I have it pulled open from Canvas. So it gives me kind of these different desired areas in the tail. Here's all my degrees of freedom. So it has it a lot more delineated here. So let's say I wanted 0.01 is the desired probability that I want the air in the tail. Maybe I'm looking for like the cutoff for the 99%. I've got a degree. Let's say I have a sample size of 34. What would my degrees of freedom be? 33 and minus 1. It's going to be a long semester if we can't do that. So we go down here. No, I forget what I said. Did I say 34 was the sample size? So we went 33 as the degrees of freedom. 2.445 would be that T value I need to get that area of 0.01 of the tail. But another nice thing about this student T table is I can always just go to the last row and it gives me my Z values associated with that. And unlike the Z table, I think I might even mention, like, if you want to go out to the third decimal, you need like a 3-dimensional Z table. Here it gives it to you out to the third decimal. So that's pretty nice. Notice at 1,000, like you can't even tell the difference at the third decimal, right? So, any questions over this before we keep? Did you guys use these in 3.7? I'm hoping. Yeah. All right. So, let's go here. So now I'm going to introduce this idea of hypothesis testing, right? So all this talk about Z and T values, why, right? Well, in practice, we can't see. If we have a sample, it's because we don't have the population data, right? Like my little NBA simulation, I had the population data. Usually we don't. We just have some random sample, right? So I use this stupid example, but let's say somebody tells me that, the average amount of money spent by IU students at the bars is, I don't know, $50 a week, right? Oh, seems a little bit high, but I go out, I randomly sample, and I find that they spend on average $80 a week. Well, I now have sample evidence that's inconsistent with what someone told me was the true mean, right? So what we're going to do with hypothesis testing is essentially there's going to be some assumed true value. That's what this mu subscript 0 is. We're going to say we're assuming that this is the population mean. I go out, I take a sample, I look at that sample mean. It's inconsistent with what I assume to be true, but is it inconsistent enough that I can reject that value, right? Because even if the true mean was 40, I could see 80 from a sample mean if I had a really small sample size. And I just so happened to get a couple people in it that were outliers, right? So it's very likely if I have a very large variance to still see values that are kind of far from these assumed true means. So we're going to have 3 different types of tests. We'll focus on one a lot in this class. So the ones we won't focus on, the names of these tests are always based off of the alternative hypothesis. So the null hypothesis, H subscript 0, that's going to be what we are assuming to be true. So the easiest one to think about probably is a two-tailed test. I'm assuming that, I think it was the value I was saying was 40 in my example, that the true mean is equal to 40, right? Usually these like assumed true means, a lot of times I'll phrase it in a way of like, because this is what we can practice. It's like, oh, the American Medical Association says the average blah, blah, blah is this. I took a sample, I found it's not, right? So this is going to be some assumed true value that we're usually trying to test with our sample data to see, does this make any sense? Okay. So we also can do different types of tests, which are the right, left, and then we call the not equal to sign the two-tailed test, right? So you can kind of think about it, I've got a greater than sign to the right, greater to the right, right-tailed or greater than test, less than sign the alternative hypothesis, left-tailed or less than test. And then not equal to sign, we call it a not equal to or a two-tailed test. Okay? Now, the reason why we call this a two-tailed test is because let's think about the difference here. So if I had a right-tailed test, what I'm saying is I've got some variable and I am assuming that it's normally distributed around whatever that assumed true mean is, okay? I then take a random sample. Sorry, I'm looking at my sample means. I take a random sample, I calculate a sample mean, and maybe I see a sample mean that's up here, right? It's inconsistent with what I assume to be true, okay? Well, I know that if I'm thinking about turning this into a t-value, the student t-distribution, that will be centered around kind of 0. What we're going to want to do is say, okay, look, I know that if I take the sample mean that I found and turn it into a t-value, so just the t-value associated with that, I can find the probability of how likely it was given what I assume to be true. If in fact this was the true population mean, how unlikely was it for me to see the sample mean I did or anything more inconsistent with that null hypothesis, right? So I'm going to go a little bit out of order, but you might recognize that kind of language as, what would this probability be called? So the probability you found sample evidence as inconsistent with a null as you did, or as many standard deviations away as you did, or anything even further away, this probability would represent what we call the p-value, right? That's just a little definition. It's the probability you saw sample evidence as inconsistent with what you assume to be true, or anything even more inconsistent, right? And this I've got drawn out. This is kind of what we would think about as we're assuming that it's less than or equal to a certain value. So then I've got greater than, we're looking at a right tail test here, okay? Now, what we're going to end up doing for a two-tailed test is not only would evidence on one side go against the null, but evidence on the other side would go against it as well, okay? So I think I've got the visual before I kind of keep doing more work here. I kind of already talked about this earlier, right? We'll take our sample mean, we'll turn it into one of these t-values. What we're now going to call that is our test statistic. You can do this if you had the population variance. You could do this for a standard normal distribution example as well. It would still be a test statistic. Generally, we just call them a z statistic versus a t statistic, right? Identifying one is coming, a test statistic from a standard normal, one is a test statistic from a student t distribution. So instead of talking about p-values first, let's think about how can I reject the null. So let's say I assume that it's exactly, the average money spent is exactly $40. I take a random sample of students, I find a sample mean of 80. Well, is that inconsistent enough? So what we're going to do is we're going to create cutoffs and say, okay, look, we're going to say there's some common thresholds. We're going to say if it was the probability of seeing the sample evidence we found, if this assumed true mean was in fact true, if that probability falls below 0.1 or 10%, then we're okay rejecting. Because it's so unlikely that what we assume to be true probably isn't true. The mean is actually probably a little bit closer to the sample mean we found. We also might want to do 5% level, 0.05, 1% level, 0.01. Okay? So we're going to refer to these as kind of our alpha values. Alpha is going to be the decimal form of these percent cutoff set, like 10, 5, 1%. We're going to kind of call alpha, that's just the probability form. So 0.1, 0.05, 0.01. Okay? Now I'll draw and look at how do these critical values and then what we end up calling our rejection region, how does that look a little bit different for a one versus a two-tailed test? But before I do that, I'm going to skip ahead. I know I have, there we go. I've got kind of one, a nice visual, and I'll draw this out again. Let's say I did have kind of this right-tailed test. Essentially what I'm doing is saying, look, I only want to reject the null. So I've got my test statistic, right? I only want to reject the null if the likelihood of seeing that test statistic is below 0.05 in this case. So I know that there is some t-value, not a test statistic, but just a t-value that is going to be associated with 0.05 in that right tail. Right? So then if I see a test statistic that's any larger than that cutoff value, I know that I can reject the null. Because any value larger than this, what's the area of my tail going to be? Less than 0.05. The probability of seeing it is going to be less than this threshold value of alpha that I set. So, excuse me. What is this going to look like for one versus two-tailed tests? We'll do a one-tailed test maybe first. And I'll use the z values here just to make it easier. We could go through, hunt through the t values for different degrees of freedom. But like I said, in practice, our data sets are over 100. So we're really going to see these standard normal values pop up a lot. So we're just going to assume we've got a sample size over 100, use those standard normal distribution values to approximate. So let's say, and this is a good point for me to time to point this out. I was writing in the notes H subscript 1. I'm trying to be better about this. When I taught lower level stats, and I did some hypothesis testing, like I had 370, I use H subscript A because it just makes more sense. I feel like when you're first learning the concept, but you H subscript A, H subscript 1. This is the alternative hypothesis. So maybe I had a right tail test here. What I'd be doing is saying, okay, look, here's my, and just for the sake of this example, like we're assuming that we have greater than 100, but we're still technically using student t distributions. We're still technically using test statistics that are t statistics. So I'll write this as a t. But I'm going to be looking at different values, different sample mean values. They should be, as long as I have a sample size over 30, normally distributed around my population mean. I'm then going to say, okay, look, I know that there is some value such that the probability of seeing something this many standard deviations above the mean, that's what these t-values represent, just like z-values, the number of standard deviations away from the mean, or above in this example. I want the probability, that cutoff, to be 10%, or the percentage of 10% probability of 0.1. What value is going to give that to me? So I go to my table, I'm using, right, the standard normal approximate value. So I go to the very last row of my student t table, and I find, if I remember correctly, I think it's 1.28. All right. So this is going to be our critical value. It's our cutoff value, right? So I don't know, critical values are great. To me, like calling these cutoff values always made way more sense, right? They're a cutoff value. And now, if I ever see a test statistic, and I'll use this terminology of more extreme, because if it's a less tailed test, it wouldn't be greater than, it's a larger negative value. So when we talk about these tests, just to make it easier, so that what I'm saying applies to every single one, I'll use words like more extreme, larger in magnitude, because saying greater and less than, well, for a right-tailed test, everything's positive. Left-tailed test, remember, our student t and our standard normal center at 0, everything be negative, and you have to like flip all of those signs. So using these words of like larger magnitude, more extreme, applies to any test. So here's my rejection region. Now, if I go out and I see, okay, here's my sample mean that I found for my sample, I turn it into a test statistic, and it's like, I don't know, 1.6. Well, this is more standard deviations away than my cutoff value for the 10% level. So I would say that with 10% significance, I can reject this null. I can reject what that assumed true mean was. I found sample evidence inconsistent enough with it that I can say that's probably not the right value, right? And it gets a little bit weird. You know, we generally don't talk about things in terms of significance when we're doing hypothesis testing, but once we get into linear regression, we generally say significance levels of 10, 5, and 1. But another thing is those kind of correspond to confidence levels. So maybe remembering from the other guys, what confidence levels would those be? So I'm saying it with like, there's a 10% chance that it's above that. There would be a 90% chance it's below it. So my confidence levels would be, did you know? Yeah, 90, 95, 99%, right? So it's basically, here's my significance level. The confidence I can say this with is 100 minus that, right? So what would a two-tailed test look like, and why would it be a little bit different? So here, 0.1 was my alpha, right? That was the desired kind of probability I wanted that was all in one tail. For a two-tailed test, what we're going to end up with is, when we want to find our critical values, yes, there is going to be, so remember I said those critical values that alpha was the probability kind of cutoff for seeing something as inconsistent with what I assume to be true or more inconsistent. The problem is now, I can see things on the right side of the distribution that are inconsistent with what I assume to be true, that know that it was equal to, specifically, exactly equal to a certain value with these two-tailed tests. So now I can see evidence that supports the alternative hypothesis that it's not equal to that value on either side of my distribution. So what we're going to end up with now is two critical values, and the total area kind of outside, or so it's more extreme than those critical values, that's going to be my alpha. Well, this is a symmetric distribution. So if I go the same number of standard deviations to either side, the area in those tails will be the same. But if I have alpha, how much is in each tail? It's not a trick question. If I have two tails and I've got alpha, how much is in each tail? Half of alpha, right? So the same size, there's two of them, right? So there's half of alpha of each one. So when I look at those tables, the tables are always telling me like the area to the left, right? So like I can look up, say my alpha I wanted was 0.1. I would have to look up 0.1 over 2 or 0.05. Now, if I use the z tables to do that, it's always kind of thinking about the area to the left. It's going to give me my negative critical value, right? If I use the t tables, I'm always kind of looking at just that right-hand side of the positive values, right? But it doesn't matter. Once I know one of the critical values, I automatically know the other. So I go to that very last row of my student t table, I look up 0.005, and I find that standard normal approximate value would be 1.65. And I'll pop the table up here in a second just to kind of show that to you. I automatically know my other critical value would then be negative 1.65. So you'll notice here, I try to choose these. Where did I put my other? Did I bury it? Yeah, I buried it. So remember before with a one-tail test, all of same level, right? Same cutoff of 0.1 or same confidence level of 90%. I can reject a one-tail test, but when I make it a two-tailed test and the idea that there could be evidence on either side that goes against the null, now notice my critical values are more extreme. It becomes harder to be able to reject the null. And in fact, finding that same test statistic of 1.6 now, I actually failed to reject the null at the exact same level. So one-tailed tests are great and they have their use. In fact, we're going to talk about something later on called the F distribution, where like you're thinking about things can only ever increase. So like then we really have to deal with right-tailed tests. But two-tailed tests are always going to make it harder for us to reject the null, right? Which is practice is good. Like we don't want to be making incorrect decisions with our null hypothesis. So when we do linear regression, we're primarily only going to be looking at these two-tailed tests. Okay, so the values that we're going to be using won't really ever change, right? Those standard normal distribution values are always going to come up to be the exact same thing, right? Those, as long as we get a sample size over 100, we can use the standard normal values to approximate. For our alphas of 0.1, 0.05, 0.01, our benchmark kind of cutoffs, we're always going to find the same three values. So those pairs, those critical values are always going to be the same. We'll see them pop up a lot. Okay. Any questions on this before we keep moving here? We're okay with this? Okay enough? Is there anything else I wanted to say here? I think I'm repeating myself at this point. Oh, I know I put this slide in. Excuse me, two reasons. And I've kind of already mentioned the one, but when we say we reject or fail to reject, we don't talk about alpha as a decimal. We generally say like percent. So we fail to reject at the 1, 5, 10% significance level, or we reject at the 10% significance level, but not the 1 and the 5, or so whatever that be. I also wanted to show you a different version of this test statistic. Because we were taking the square root of something squared, sometimes you'll see that denominator written a little bit differently, because the square root of something squared just cancels as itself. So you might see your test statistical equation kind of written a little bit differently like this as well. I also had a question. I will get up. I'll get this up this afternoon. And it's going to have stuff that doesn't make any sense right now. But for the exams, you will have a formula sheet. I think I failed to mention that at this point. A lot of these formulas we're going through, you will have a formula sheet for the exam to kind of use. Okay. This will be one of them. Also, I apologize. My voice is third class in a row today. My voice is finally starting to go a little bit. So we already did this. So here's kind of the general steps to the critical value approach. Where are we at on time? Right up where I want to be. So in general, figure out your null alternative. Like I said, for this class, for the most part, I'm just going to expect you to do these two-tailed tests, because those are the ones that we're going to rely on throughout this semester. Okay. Specify the alpha. To find your critical value, you need to know what alpha level you want, right? What's that significance level that you want? You want the probability to be 0.1, 0.05, or 0.01. You could do different ones. It's just the three benchmarks we're just going to consistently use. These two steps are really interchangeable, because I can find my test statistic and then my critical values, or I can plot my critical values and then my test statistic, right? It doesn't matter either way. But once I have those, you don't have to draw it out every time. I just think it's nice to have a visual. It makes it kind of easy, because it does get kind of tricky when we're dealing with the negative values. And I think here I skipped over this that I have here. Yeah. So I'm going a little bit out of order. But when I'm dealing with like the left-tailed tests, notice how like the signs would flip. Really, your test statistic only ends up in your rejection region if it's more extreme than your critical value. So when they're both positive, that's when it's greater than. But when you're looking at the negative side, then your test statistic to be more extreme is actually a larger negative value or less than. So a good rule of thumb, no matter what hypothesis test you're doing, one, right, left-tailed, two-tailed, always just take the absolute value of your test statistic and your critical value. So you heard this term absolute value before, just familiar with for most of you. All that means is get rid of the negative sign, right? So this means take the absolute value when I kind of put these two bars around these statistics. So once you take the absolute value, it's just telling you the magnitude. If the magnitude of your test statistic is greater than the magnitude of your critical value, you reject. Okay? And like I said, I'll use the terminology of if it's more extreme. I think that makes a lot of sense as well. But yeah, when you are dealing with those negative test statistics or negative critical values, it's kind of tricky. Always just take the absolute value, and then is your test statistic more standard deviations away than your critical value? And it helps to think about your critical value is the cutoff. Basically, if I find sample evidence that's more than 1.65 standard deviations away, then that's too far. What I assume to be true can't be true. So if I find a test statistic that is more than, right, or kind of in absolute value or in magnitude larger than this cutoff value of 1.65, then I'm okay rejecting. Okay. Any other questions up to this point before we keep moving? Okay. Let me think. So we've got our steps here. I don't think we're going to do this. What I think I want to do, I say what I think, I know what I want to do, is go here and give you a taste of kind of what these in-class quizzes I'm going to use are going to look like. So we're going to change this to be today. And we want it to be, oops, 12:30. And I want to have this close out. Now, you won't always set it at the end of class. If we do this in the middle, you know, I might only open it for like 10 minutes. But for today, no, not 11:30. We'll have it be to the end of class. Okay? So the next 15 minutes, you now get on Canvas and you go to quizzes. I don't have it added into the homepage. So go to quizzes. You should see this in-class quiz number 1. You won't see this other stuff because I don't have it published, right? So in-class quiz number 1, click on it. You should just open up. I have my instructor view on, so I have to go to preview to get into kind of student mode. Okay, here's the quiz, all right? Now I am actually using this, so you should be getting on Canvas right now, and you're gonna have to answer these questions, right? So we didn't get to problem 1 quite yet, but we did get to question 2, okay? So what I would generally do is say, okay, look, take the next 5 minutes, maybe 10 minutes, depending on, sometimes I'll give you 3 questions or something. I want you to answer these questions, right? Talk to the people around you, you know, work on this. I'll let you know, when 5 minutes is up, then you'll hit submit, and then we'll kind of talk through them, right? And when I say you'll hit submit, in practice, like, you actually are going to have to get the correct answer. I'll have it set to close. So like, let's say I gave you 5 minutes, I would set so it closes in 5. So it's not like you can continue to work on it after we start talking about it, right? So I'll have it open for a very short period of time, allow you to work on it, get your answers in, submit it. I'll then kind of wait until after, closed out after the end time. We'll then talk about it in class. I saw a question.
Yes, so do you want us to just answer?
Don't worry about question 1. As long as you respond today, I have a way to kind of go back in and just give everybody credit for it. Yep, you don't have to respond to it. What I would have you work on is question 2. Okay? Now, I'm going to be kind of nice today. We'll just work through this together. So hopefully if everyone's paying any ounce of attention, we'll all get this correct. All right? And I also typically will do something like this where, yeah, if you didn't get them right, you're at least still getting half of those participation points of the day. Just click on that yes to kind of earn, and I put extra credit. This is just the additional, this shouldn't say extra credit, I don't know why it says extra credit, but just the like participation credit for getting. Extra credit makes it sound like it's additional. It's like just the free credit on this one. Okay. So this will be kind of what the format looks like. So we'll work through this one together. Like I said, hopefully everyone gets this correct. It's basically an entire hypothesis test, okay? So if I assume that the mean IQ is 105, right? I'm assuming that it's equal to 105. I've got a 2-tailed test. I'm assuming it's exactly equal to 105. I take a sample of 50 people. I get this sample mean IQ of 102. And let's say I somehow knew the population variance so that we can just use the standard normal distribution, right? Making this one a little bit easier. So I've got population variance of 144. What levels of confidence could I reject and null at? So I tried to use the chalkboard in my other class and realized I am way more efficient using this. So we're going to do this. So I've got my sample means, right? I know they should be normally distributed around whatever that assumed true mean was, which you got pulled up. I forget, what was the assumed true mean? Was it 105 or 102? 105. So that's going to be where we should be centered around. Right? I then can say, okay, look, what are my 3 critical values, right? Well, I've got a 2-tailed test, so I know I'm going to have 3 pairs. I've got 0.1, 0.05, and 0.01. So if I go to that very last row, I look up those 3 values, and those are the t-values they use, right? I just look at my alphas for a two-tailed test? No, right? For a two-tailed test, alpha is going to be the area total in my tails. So when I go to the table to look up the area that I want in that one tail, I actually want to look up alpha over 2. Right? So instead of looking up 0.1, 0.05, and 0.01, which are my alpha values, I'm looking for the critical values that give me alpha totals in the tail. So half of alpha is in each tail. So I'm actually going to be looking up the values of what? 0.05, 0.025, and 0.005. Okay. Now, I'm going to go over here real quick. If I go down to this last row, looks like it's what? Whoa, went way too far. It's going to be these 3 columns, right? 0.005, 0.025, and 0.05. So it's 1.645, 1.96, and 2.576. I'm going to just round these to the second decimal. So this was 1.65, 1.96, 2.58, I think, if I'm remembering those correctly. So my very first one, I can say, okay, look, here is the critical values associated with an alpha of 0.01 or the 1% significance level. What do I next need to do? Well, I need to know what my test statistic is, right? So we found a sample mean of what? 102. So if I want to calculate my test statistic, I'm going to take that sample mean that I found. I'm trying to figure out how many standard deviations away from the assumed true mean it is. So what do? I subtract that assumed true mean and then divide by the standard deviation of those sample means, which is the square root of my original variance from the data I sampled from, which was what? Divided by my sample size, which is, so if I do this, anybody want to help me out? I think from memory, I think this is negative. I might be flipping my 7 and my 6 here, but I think it's negative 1.76 or 77. Yeah. So here's my test statistic. So if I'm thinking about where does that fall? Visually, oh yeah, it's not quite in my rejection region at that 1% significance level. So I failed to reject at the 1% level. Well, what about the 5% level? Well, there my critical values, and I leave myself a lot of room, but there my critical values would have been positive and negative 1.96. Not quite, right? I'm still not quite in the rejection region there either. Well, what about the 10% significance level? Well, there looks like my test statistic of negative 1.76 would be in that rejection region. Or if you don't want to draw this out, what you could have done is said, okay, look, I found these 3 critical values. I know that if I'm comparing the, well, I don't have a lot of room here, so let me move this over. If I'm comparing my test statistic and I look at the absolute value of it, I only reject if that is greater than the absolute value of my critical value. So what were my 3 critical values? They were 1.65, that was for my alpha of 0.1, 1.96, alpha of 0.05, and then 2.58, my alpha of 0.01. So I now look at my test statistic. The absolute value of it was 1.76. Is that greater than 1.65? Yes. So I can reject. It is not greater than 1.96. So I fail to reject. It's not greater than 2.58. So I fail to reject. So here, I'm only able to reject at that 10% significance level. Okay. So with this idea in mind, could I ever only reject at the 1% significance level? Well, if I'm rejecting at the 1% significance level, what has to be true? My test statistic would be greater than 2.58. How could my test statistic be greater than 2.58, but not greater than 1.65, right? So it always kind of works out that you can start to reject at higher significance levels, which correspond to lower levels of confidence. I might be able to reject with 90% confidence, But then as I want to say things with higher levels of significance or higher, sorry, as I want to go say things with higher level of confidence or lower significance values, well, it might be harder, right? Because now my cutoff values start to get really large. Now maybe my test statistic won't be greater than that, okay? Any questions, kind of anything that we just worked through here? So hopefully we saw that we rejected at that 10% level. This is, like I said, a lot of times I see you guys really working. I might work through it with you, or at least work through a lot of it. And hopefully, if you're paying any ounce of attention, you can then very easily make sure you're getting the correct answer here today. So I still am grading it for correctness, even though we worked through it together. That shows me that if you didn't get it correct after we worked through it, you might have just been here, but you weren't actually here in class, right? Okay, so don't worry about question one. Like I said, I can kind of just look at who responded. I'll end up in the back end kind of giving everybody credit for that question one because we didn't have quite enough time to cover confidence intervals. So next week, what I want to do is we're going to kind of pick back up. So let me go back to the slides. We'll talk a little bit about hypothesis testing, some type 1, type 2 error stuff. We're going to talk about some things that impact whether or not we can reject the null. I'll walk through a different approach, which is what we call the p-value approach. We'll talk a little bit about confidence intervals and connect those to the idea of hypothesis testing. I know in 370, you probably learned them in the opposite order. You'll see why maybe there's a point I really want to make about confidence intervals for how we'll use them this semester, but it makes a little more sense first to have like hypothesis testing and confidence intervals. Excuse me. Other than that, like I said, 10 to 1 tomorrow, Monday, office hours. We don't have any more holidays, so 12:30 to 3:30 back as usual. Please, we got to get these kinks with Stata worked out for everybody. So if you're still having trouble, stop by or set up a time to meet with me via Zoom during those times. Other than that, start working that first problem set. Once you see it pop up, that next quiz will be up after class on Tuesday. All right? Have a fun, safe weekend. I will see you guys on Tuesday. Hey. Yeah.